Okay, I hope you enjoyed that demo. Hopefully it gave you a sense that you can't just blindly take code off the internet and shove it in your project because it might have issues in it, and we talked about what those issues were. So we talked about variable scope a little bit. We talked about locals and how they're on the stack, and those are the most common, and those are the most safe. That's typically how you want to use variables. When you enter a function, everything that can stay there in that function, do it right there, and then when you leave the function, it all goes away, and then there's no state you have to be overly concerned about making sure you remember to free this or that. All local variables go away on their own when the function returns. There's also, of course, global variables, and they're very useful because they can be used across your project, but you want to use them sparingly because they're a bit more dangerous. You can run into various issues as they're accessed from different spots in your program. There's different types of static variables. Static global is visible across the file. Static local retains local variables across calls to the same function. And a static member in C++ is shared across instances of a class, so pretty much a global in C++. We'll talk about that later. And there's some keywords in C that are interesting, like the keyword volatile is a qualifier that's applied to a variable when it's declared. It tells the compiler that the value of the variable could change at any time without any action being taken by the code near it. So the compiler should leave that alone. It shouldn't optimize it out, for example, or something. There's also the extern keyword, and it applies to both variables and functions. And it extends the visibility, for example, global variables that you need to use across files in a project. So here's another example of a variable called a structure. We've got a database here, and it's got an ID number, an age, and a salary. And you can declare that struct database employee. You can define the employee locally as it's done here, so it's on the stack, .age is 23, ID number, salary, whatever. Or you can make an employee pointer, malloc some memory for it, and then you use the arrows rather than the dot to assign values to that structure. But now remember, since we just malloced memory, we need to remember to free it as well. That's one of the trickiest things in C is memory management and memory corruption, and we'll be talking about those more. So here's a good example of a memory leak that you might find online if you're looking for examples of reallocate online. Realloc is a way that you can change the size of a buffer dynamically. But if realloc fails, it returns null. So the reference to the initial malloc pointer is lost, and then you don't have a way to free it. So with all of these, with malloc and realloc and any of them, you should explicitly check for failure conditions and make sure your code is doing the right things in all cases. So the standard and extended C8 libraries have just loads and loads of APIs, but here's a few that you'll bump into pretty often. Things like copying strings, comparing strings, checking the length of a string, all that kind of stuff. Those are common ones that you'll run into. Printing to the standard out or to buffers are quite common things that you'll want to do. Copying data, reading and writing from a file, checking the size of an element, very important things to do on data. Being able to fork or exec a process is very important. And opening, writing to, closing files are things that are commonly done. If you want to see exactly how any one of these works, you can just, on a Unix system, you can type man space fopen, for example, and it'll give you the manual page for fopen, or you can just type that into Google too. You can type man space fopen and you'll find the manual page online. The last thing I want to talk about in this module is socket programming. There's a few reasons I want to cover that. First of all, it's an interesting homework assignment because socket programming has been around a long time, so it's interesting looking code. Secondly, if you ever compete in any security hacking competitions called capture the flag events, a lot of times what happens is, and there's a lot of different ones, so you might end up with challenges that are sort of like web hacking or forensic challenges or exploitation or scanning or whatever it might be. But if you're doing some of the reversing and exploiting challenges, they'll often give you a server and you have to find the vulnerability and either patch your server or write an exploit to attack somebody else. And so what's interesting about that is you want to be able to do that as quickly as you can. And so being able to understand socket programming, when you're looking at the code in a disassembler like IDA Pro, you can go, this is all not important because it's all just socket programming. I need to find the code that actually processes data that comes across the network. And I'll show you how to do that right now. So these examples are going to be for Unix-like code. Native Windows networking code uses specific Windows APIs, but it's the same idea basically. What you need to do is initialize some structure, in this case a sockadder, create a socket, and then connect to the server if you're the client. If you're the server, you need to initialize a structure, create a socket, and then bind, listen, accept. It's a pretty simple idea, so let's just walk through the code. Here's the sock adder structure, 16 bytes in size traditionally, and the sock adder in overrides that more specifically to break down the family, the port, and the IP address. The in adder is a 4-byte value that holds the typical IPv4 IP address. So to declare a sock adder in locally, we just say struct sock adder in adder, and then we can do adder.family equals IPv4, adder.port equals H2NS, A to I, argv2. What does that do? Well, argv2 would be the third string on the command line argument. The 0 would be the program name, and then 1 would apparently be the IP address, and 2 would be the port. If you're connecting, giving a program like netcat or telnet saying connect to this server at this port, that's how this would get done, something like this. So we convert the string from an ASCII to an integer, and then we change the byte ordering from host to network short. Then we use the inet adder API to convert the dotted decimal 192.168 whatever IP address into the internal packed 4-byte value. Then we call socket on a sock stream to get a TCP socket. Then we can use the connect API to get our file descriptor, and we pass in this adder structure that we've already defined, and it looks a little goofy, you notice. The struct sock adder star is typecasting the local variable, and we need the address of that to be of the type of this pointer that the API expects. And we need the size of it as well, which is 16, or better programming practice to say size of rather than hard coding a value 16 in case that were to ever change. And if it fails, we can ask the operating system through a syscall, PR, what happened. And the system might say something like connect, no route to host, something like that. And one of the things you notice right off the bat here about the return value, the if connect equal -1, one of the unfortunate things about C is that the return values aren't really standardized. So in many cases, 0 or 1 represents success and -1 represents failure. But that could be flip-flopped or you know, there's no standard. It doesn't have to be that way. One API might do something different. So you kind of have to know every API what they do. So you have to check the manual page and see what does it return. From the server side, the first thing we do is bind to set up the server FD, and we pass in the server structure. Same thing with PR. Then we can do listen and specify a maximum length to which the queue of pending connections for socket FD could grow. And then finally, we can do the accept. So you probably have some kind of while loop where you say FD equals accept, server FD, and then the socket structure and the size. So based on the listening socket, you're going to get a new socket for every incoming connection. And then what you want to do so that the server doesn't get stalled handling any one connection is you want to fork a new child process, or in Windows, you'll create a new thread, same idea, multi-process application going. We'll see that fork returns 0 in the case of the child process, and it returns the PID for the parent process so that you can print out the child process ID. And then the reason I've highlighted the handle client code is because, again, if you go back to that capture the flag example, that's the code you want to focus on. That's going to be the code where if there's any bugs that you could exploit remotely when you send data or something to the server, that's where that code will be. All the other code is just setup, socket, server type handling, connection code that really, if there's a bug or something in it, this simply won't work. It's not going to be a security vulnerability. So learning where to find and key in on the attack surface is a very important skill that any code auditor should have. So in this first module, I provided kind of a whirlwind tour of the C programming language, particularly as it relates to security. And I've talked about some of the different nuances and all the little gotchas and some basic bugs that we saw as well. Finally, we talked about some socket programming, and the code examples that are available for download as part of this course include that socket program. And what you should do for your homework is download that, check it out, compile it. There's a simple bug in there. See if you can find it, have fun with that, and we'll talk to you in the next module.